Okay, just copy the first one and the last one. The one in the between, that one is okay. Just dot, dot, dot. Okay, next, this one. Okay, so same thing. You see, express both numbers exponential form first, right? Then keep applying your laws of indices until you reach the final answer. Okay, so this is how you do it. Okay, and this is also why I said just now you will grow to love exponential form. Because you can imagine trying to multiply this number in Cartesian form. How will you multiply this number in Cartesian form? You have to cube the 1 plus I first, right? Then you apply binomial theorem. Then you have to apply binomial theorem again for the power of 4. And then you're not done, you know. You have to do expansion. Okay, so learn to like the exponential form. Now you may dislike it. It's natural. I expect that. Okay, but you have to learn to like it. Alright? Can Okay, but then there's also another reason why this works. This works because the angles involved are special angles. If they are not special angles, the exponential form also cannot really help you. Okay? Okay, let's go on. Okay, this one, same procedure. Okay, first, you attempt. Not attempt, you proceed. It should only be attempt. You must do it well. Okay, you proceed to find both complex numbers in exponential form. Okay, so you can only do that after you have found the moduli and the arguments. Okay, next. Okay, put everything together. All right. Cannot. Just copy the modulus and the argument will do. All right. Okay. Okay, the next slide, the first part there is exactly the same. Just that it's more summarized, that's all. Okay? Same thing, Same thing. Same thing. Not I going too fast, it's the same thing. Okay? Okay, now, so I have to first find the modulus of this number. Or you can do it in the previous way. You express both 1 minus I square root 3 and negative plus I in exponential form first. Okay, then you put it in, repeatedly apply law of indices. Okay, this is another way. This is you look at the modulus and the argument separately. Okay, so the modulus of this very large complex expression, okay, would be as such. Right, so I'm applying the laws of the modulus that I showed you just now. Those that say what? Modulus of Z1 times Z2 equals modulus of Z1 times modulus of Z2, so on and so forth. Okay? So I simplify this further. I'll get, okay, you cannot see that properly, it's 16 square root 2. Okay, 16 square root 2. Okay, now I've obtained the modulus, I've obtained half of the exponential form already. Okay, I've obtained half of the exponential form already. So now I need to find the other half by finding the arguments. Okay, so argument how to find? They work exactly like what I said, logarithms. Right, familiar, right? Okay, that's how your logarithms work. Okay, then you solve. Now you get another angle that is again not in the principal range. Now is it too small or too big? Too big. So negative still too big. Too small. So you add 2 pi. Okay, but this time round you add 2 pi, not enough. You add 2 pi already, you are only going to get negative 9 pi over 4, which is still out of the range. So I must add 2 times of 2 pi. Sometimes they can become so negative. also positive. Okay? Okay, then you see again, congruency symbol. Later on, don't worry, common test confirm a lot of people put equal sign, the presentation mark all gone on. I'm foreseeing it already. Okay? Right, equals to negative pi over 4. Okay, so, okay, you pause for a while because I'm going back to the previous slide. No, I'm going too fast. Okay, previous slide. Okay, so the modulus of this very chunky number is 16 square root 2. Okay, the argument of this very chunky number is negative pi over 4. So the exponential form is thus 16 square root 2 times e to the power of I times negative pi over 4. And please put in the brackets. If you don't put in the brackets, it will read to me as I minus pi over 4, which means totally different. Okay, so when I mark, and mathematically speaking, it means something totally different to me, it will not even be a presentation deduction. Is that serious? So please don't play a fool when it comes to your brackets. Okay, don't always expect your teacher, presentation, I can afford to lose my presentation marks. Actually, you cannot afford to lose your presentation marks. Okay, it could be a 1 grade difference. All right, now, polar form, same thing, or similar thing. Okay? Can Okay. Anyway, it's recorded. So, okay, it's recorded. Just that I take a bit of time to upload. Alright? Okay. Okay, now let's look at multiplication geometrically. Alright? Okay, now in the previous lecture, right? Listen. Okay, I've discussed with you addition and subtraction of complex numbers geometrically, right? You remember how that worked? Okay, so how that worked was we viewed them as vectors, then we applied vector addition and subtraction, but there was also the catch that I mentioned that you have to bring them back as position vectors. Okay, now so I'm going to use exponential forms, okay, to explain to you the geometrical effect of multiplication. Okay, so suppose I have a complex number z, okay, represented by this point pz. Okay, now what happens if I multiply this complex number by a real number r? Okay, or rather a positive real number r. Do you know what's going to happen? What's going to happen to my point pz, okay, after I multiply the z by a positive real number r? So where is p? Where is the point representing rz? Where is it? Further away. So I'm going to extend out my line segment, okay, scaling by a factor of r, which is exactly what you will see on the real number line. Right? From 2 to 6, the distance increases 3 times. Increases by 3 times. Okay? But now in the Argand diagram, you have to follow the direction of the line segment when you extend. Alright? Simple? Okay, now. Okay, so this is if I multiply by a positive real number r. Now what is going to happen if I multiply by a complex number? Okay, so to keep things simple, let me assume I'm going to multiply by a complex number whose modulus is 1 first. That means r equals to 1. Okay, so I'm going to multiply z by ei theta. Okay, now let's suppose this is the argument of z. Okay, and I multiply z by ei theta. Okay, so what you're going to see here is a rotation. Okay, why is that so? Now, if I take this number, I find its argument, right? You apply so-called like a law of logarithm. Okay, in this case, we call law of argument. Okay, you're going to see this result. Okay, so in other words, the effect of multiplying ei theta is adding the argument by theta. Okay, so I'm going to see, let's do it again. I'm going to see a rotation, okay, by theta radians. Theta radians, okay? So this is where the point representing EI theta times Z will be. Okay, so what can I conclude? So if I want to multiply by a complex number in general, a complex number REI theta, right? Okay, so what I'm going to see is this. The effect is this. I will first rotate the light segment by theta radians. Okay, keeping in mind it should be dash. Okay, then extending the modulus by R. Okay, the modulus by R. Okay, so you will see this. All right, you'll see this. Okay. Can Okay. Okay, this one I will not go through. All right. Okay, this part about the geometrical effect of multiplication is also illustrated on page 16 of your notes. Okay, again, why I skip? Because I know you don't like us to skip here, skip there. Let me rationalize it for you again. Because much easier to use exponential form to explain than polar form. That's why I skip. Okay, so you go and read the page. There are some specific examples. Okay, then example 7.3.3, I will not go through. Okay, it's not given to you. The solution not given to you, but it's okay. Okay, later on you just check the teacher's version. All right. Okay, then with that, I end my lecture. Okay, next lecture we will continue with the loci. Okay, loci. All right. Loci, not loci. Okay, loci. Okay. Okay, so bring that lecture notes. What? No, not erase. Done. Okay, the two students who I asked to meet, please count down now. The rest you may leave already. All your complex number lectures so far have been recorded and uploaded. So you got any queries, you can go back and refer. All right.